I'm Ben Eisenbach. I'm excited to share a paper, a connection between one-step regularization and critic regularization in reinforcement learning. Offline or batch reinforcement learning is exciting because it would allow a reinforcement learning agent to learn how to take good actions purely from historical data without needing new exploration or interactions with the environment. Most offline RL algorithms learn an actor and a critic. Critic predicts the future returns, and the actor maximizes the future returns. Effective offline RL algorithms would unlock applications from autonomous driving to healthcare to education, applications where we really don't want to be doing trial and error learning. There's been a lot of really great work in offline RL, especially over the last few years. There's been so much great work that it's been hard to see the connections between these methods. This paper explores one connection. Broadly, I'm going to group offline RL methods into three categories. One-step RL methods, methods like weighted behavior cloning, are generally pretty simple. Critic regularization methods, including methods that learn ensembles, are a bit more heavyweight but can achieve really great results. There are also some methods that regularize both the actor and the critic, methods like KL control. In theory, you can make hybrid algorithms by mixing and matching the components, but most prior work lies on one of these three islands. The main contribution of this paper is to show a connection between one-step RL methods and critic regularization. This connection is surprising because these methods look pretty different on the surface. And it's also useful because it will allow us to make testable predictions about how these methods behave. I'll start by reviewing how these methods work. While most reinforcement learning methods do many steps of policy improvement, one-step methods just do one step of policy improvement. This is a bit like early stopping and can be seen as a sort of regularization. Because these methods just do one step, they're pretty cheap in terms of computation. They have some other properties I'll mention later. Critic regularization methods, on the other hand, regularize the critic, so it predicts lower values for unseen actions. These methods do many steps of policy improvement and can be a bit more computationally expensive. They have some nice properties about how they propagate regularization across time and about how they underestimate the future returns. The main contribution of this paper is to show that these two methods can coincide. We prove that for a certain degree of critic regularization, these methods produce the exact same policy. And this occurs when critic regularization uses a certain regularization coefficient of 1. Now, our results require some assumptions on how these methods are implemented. The reason this theoretical result is surprising is that on the surface, these methods appear quite distinct, even if intuitively both are motivated as avoiding unseen actions. For example, while critic regularization is a multi-step reinforcement learning method, this result says that there is sometimes a shortcut where you can get the same answer using just one step of policy improvement. It also suggests that these methods might share certain properties. We've also extended our results to goal-conditioned problems as well as other problems. First, to check that our theoretical results were correct, we applied our method to a tabular setting where we could ensure that our assumptions hold exactly. We see that the policy produced by critic regularization and one-step RL are exactly the same. We next look at a more realistic continuous control task and use implementations of real methods. These methods violate our assumptions. Now, based on our theoretical results, we predict that one-step RL methods might have the same lower bound property that critic regularization methods have. And empirically, we find that this is correct. The Q value underestimates the true future returns. Our theoretical results also suggest that critic regularization methods implicitly regularize the policy. Again, the experiments confirm this prediction. So in this paper, we showed a connection between two common sorts of offline RL methods. This connection is useful because it suggests that some of the differences in performance might come more from implementation decisions rather than differences in the objective. Very broadly, I'm excited about this because we no longer have to be isolated researchers working on siloed algorithms on lonely islands. And by bridging the different sorts of regularization methods, we can better understand their strengths and weaknesses. The paper has more results about our theoretical results. One final note. I mentioned earlier that there's this third class of methods, which our paper didn't analyze. An anonymous paper recently showed up on Open Review. An Appendix C of that paper gives some hints that this third class of methods, it might be closely connected to critic regularization. So it seems like there's some really neat and deep connections between all of these sorts of regularization methods. Please stop by our poster to learn more about this. Thanks.